So today it's my pleasure to welcome Akhila Palat to present us the presentation titled Evaluation of Geomechanical Behavior of Fiber Reinforced Clay Soil. Akhila completed her Bachelor of Technology degree in Civil Engineering and a Master of Technology degree in Geotechnical Engineering from India. She moved to Canada in 2017 to pursue her doctoral degree at the University of Alberta under the supervision of Dr. Michael Hendry. Her present research interests include the effect of varying fiber content and structure on the strength and pore pressure response of soil fiber composites. Akhila is also a member of the Canadian Federation of University Women and the Edmonton Historical Board. I think this is going to be a great presentation, so I will stop right here and let Akhila take the stage. Thank you.
Good afternoon, everyone, and thank you so much for your time. Without any further delay, I'll start my presentation, Evaluation of the Geomechanical Properties of Fiber Reinforced Clay Soil. Previous study for soil already proved that adding short discrete fibers increases the strength, stiffness, and ductility of the composite. But most of the existing studies are done on fiber reinforced sand, and a very few have been done on the fiber reinforced clay soil. The potential applications of this composite would be in the repair of field slopes, land reclamation projects, landfill liners or final covers, and in the stabilization of mine waste tailings. Moving on to the objectives of the study, the primary objective is to analyze what is the role of polymer fibers in altering the geomechanical behavior of clay soil. Then to examine the role of sample preparation techniques, basically compacting the soil to its optimum moisture content and placing hydraulically as a slurry, and changing the length of fibers on the shear strength and pore pressure response of the composite. Implementation of the fibers within the fiber reinforced clays prepared using the compaction and slurry method, and evaluate what is the extent of anisotropy exhibited by this composite. Finally, to discuss the limitations of the traditional triaxial compression test in quantifying the strength of this class of material. Moving on to the materials, the clay soil adopted for this study is manufactured by Edgar Minerals, and these are the properties of the clay as determined from laboratory testing. The fibers used were pre-cut polypropylene fibers supplied by many fibers, and these are the fiber properties as provided by the manufacturer. Synthetic fibers are used for this study because their properties are easily controllable, and we can get the pre-cut ones from the manufacturer. 3 lengths have been tried in this research and 48. One of the most challenging aspects of this study was to prepare homogeneous fiber reinforced clay samples for triaxial testing. In this paper, we are discussing 2 potential options for preparing the fiber reinforced clay soil for lab testing. The first one is the compaction method, where the soil and fibers were mixed with water at its optimum moisture content, that's 28%. And to prepare samples, the soil fiber lot was placed in the 2-part compaction mold as 5 layers, with each layer subjected to 15 blows using a rammer and an arbor press. In the slurry method, the dry kaolite clay and fibers were mixed with a large volume of water, approximately 2.5 times the liquid limit of the clay soil. That comes around 145%, and this bulk volume of water is required to make sure the slurry has a flowing consistency and there are no lumps formed in the clay soil. The fiber soil slurry was left for sulfate consolidation for 2 weeks under the conditions of double drainage. Following that, it was loaded from the top incrementally to a pressure of 100 kilopascal. 2 Shelby tubes of 50 millimeter diameter were pushed into the soil fiber block using the mechanical press, and cylindrical samples were extracted for triaxial testing. So the first image shows a compacted fiber reinforced clay, and the second one shows a slurry fiber reinforced clay composite. Moving on to the testing methodology, all tests in this paper were consolidated undrained triaxial compression test because the major objective was to measure what is the undrained shear strength and induced pore water pressure developed within the composite. Previous studies by the authors proved that the optimum fiber content for mixing is 2%, and any increase in the fiber content beyond 2 resulted in a reduction in the strength and pore pressure response. So for all tests in the study, the fiber content is kept constant at 2%. The other variables of the testing program are 2 methods of sample preparation, 3 lengths of fibers, and 3 values of effective confining pressures. To determine what is the orientation of fibers within compacted and slurry samples, we developed a novel fiber-reinforced transparent soil. So the principle behind a transparent soil is that the soil and pore fluid combination will be of matching refractive index, so that appears homogeneous to light and it becomes transparent. Previous studies on transparent clay already proved that fumed amorphous silica has properties consistent with the properties of natural clay. So for this study, we used fumed silica and a combination of white oil and process oil to develop our transparent clay. In silica and pore fluid was kept constant as 6:94, and the ratio between white oil and process oil was kept between 77:23. These ratios were selected based on the transparency of the final mixture. Pre-cut 10K geotextiles were used to reinforce this transparent clay to prevent the color from synthetic fibers mixing with the clay soil. Moving on to the results, all unreinforced clay soil failed by forming a well-defined failure plane. But in the case of the fiber-reinforced sample, a bulging response was observed. This is expected due to the movement of fibers to these planes of weakness and mobilization of tensile stresses. When we compare these two pictures, greater amount of bulging was observed in the slurry sample, and that is expected due to the greater freedom for the fibers within the slurry samples to move and mobilize tensile stresses. Moving on to the effect on deviator stress. So in all these plots, the faint lines, these ones are for compacted samples, and the bold lines are for slurry samples. For all 3 lengths of fibers and all values of confining pressures, compacted samples demonstrated higher values of deviator stress compared to the slurry samples. This is because the compacted samples are prepared at their optimum moisture content and maximum dry density. The density of the compacted samples varied between 1.85 to 2 gram per cc, whereas the density of slurry samples varied from 1.5 to 1.6 gram per cc. This increased density and tiny particles resulted in higher values of deviator stress within the compacted samples. For the range of fiber lengths used in the study, any increase in the length of the fibers resulted in an increase in deviator stress in the compacted samples. But for slurry samples, a reduction was observed in the Q value when the fiber length was increased beyond 18 millimeter. This is expected due to the scale effects factor, probably because of the greater tendency of the 48 millimeter long fibers to get bent and twisted inside a 50 millimeter diameter specimen. So we recommend testing on larger diameter samples to confirm the effect of varying fiber length on the deviator stress in slurry specimens. Looking at the effect on pore water pressure response, for all compacted sample, the pore water pressure developed within the composite reached a maximum value at lower values of axial strain followed by a steep reduction. This behavior of a heavily over-consolidated soil is due to the higher compaction energy supplied during the sample preparation. But for all slurry samples, the pore water pressure increased, reached a maximum value, and it remained unchanged throughout the shearing. This is due to the increased amount of tension that is mobilized in the fibers within the slurry samples, resulting in an increased pore water pressure response. When we observe this graph, for all values of confining pressures, the pore water pressure developed at the end of the shearing in 18mm composites was equal to the effective confining pressure at which the sample was sheared. And the probable reasons will be discussed in the subsequent slides. Moving on to the evaluation of effective stress path. The undrained effective stress path for an isotropic material is vertical. Any deviation from the vertical indicates the presence of anisotropy within the sample. Again, if the effective stress path deviates to the left with a negative slope, it means the sample is stiffer in the horizontal. When we compare these three plots, for all lengths of fibers, as soon as the shearing is initiated, the effective stress path for the slurry samples deviated to the left. This indicates an increase in the overall horizontal stiffness of the slurry composite compared to the vertical stiffness. For 18mm long samples, the effective stress path approached the tension cutoff line and later followed the trace of this line. The amount of tension mobilized in 6mm long fibers were less because of their shorter length, and the amount of fibers in 48mm long fibers, the amount of tension is less due to the scale effects factor that we discussed previously. So this change in the slope of the effective stress path for the slurry samples and the compacted samples is mainly due to the change in the orientation of the fibers inside the composite. In order to determine how the fibers are oriented within the slurry samples and the compacted samples, we have our study on fiber reinforced transparent soil. So this is the setup that I adopted in the lab to capture the images of the fiber movement during soil consolidation. Continuous images were taken using a Canon camera that was connected to the computer and with an EOS utility software that was installed in the computer. So continuous images were taken every 30 minutes to track how the fibers move during soil consolidation. It was really challenging as any intrusion of air bubbles into the solution will make my transparent soil completely opaque. Another issue that I faced was the color from these fibers mixing with the solution, and as you can see over here, I can see nothing. That is the main reason why we decided to replace the synthetic fibers with the geotextiles as they are more durable. So this is the image on day 1, which means how the fibers are oriented as soon as I prepare the soil fiber slurry and pour it to the glass mold for consolidation. As you can see over here, there are some fibers oriented in the horizontal direction, some in random direction, and even there are some in the vertical direction. At the end of self-weight consolidation, some of the fibers developed a tendency to align in the horizontal direction. And once it was consolidated to 100 kilopascal, as you can see in the final picture, majority of the fibers aligned in the horizontal direction. So if we cut Shelby tube samples from this soil fiber slurry and perform triaxial compression testing, the fibers are already aligned in the horizontal direction. Tensile stresses starts to mobilize in the fibers as soon as the shearing is initiated, increasing the overall horizontal stiffness of the composite. Now moving on to a compacted fiber reinforced transparent soil. This was prepared in the same way as we prepared a compacted kaolinite clay polypropylene fiber specimen using the 2-part compaction, mold, rammer, and an arbor press as 5 layers with each layer subjected to 15 blows. So this is my compacted fiber reinforced transparent soil. As we discussed before, this looks opaque due to the intrusion of the air bubbles. So the compacted specimen was placed in a glass beaker and a pore fluid combination of matching refractive index was poured from the top. So this pore fluid combination and the clay soil as a refractive index matches it appears transparent, and here we can see how the fibers are oriented within a compacted specimen. There are some fibers which are oriented in the horizontal direction, some are oriented in the vertical direction, and some in the random direction. Now, attempts were made using the polyline detection tool in MATLAB to get the inclination of each and every line within the slurry soil as well as within the compacted sample. And this graph over here shows the probability distribution chart for slurry samples as well as for the compacted samples. We can say within a compacted specimen, there are fibers which are oriented between 0 degrees and 90 degrees, and there is a greater probability of finding a fiber which is inclined at 45 degrees to the horizontal. Whereas in slurry samples, the fibers are oriented between 0 degrees to 40 degrees, and there is a greater likelihood of finding a fiber that is aligned at 20 degrees to the horizontal. This shift in the normalized probability distribution chart to the left in slurry samples confirms that the majority of fibers are oriented in horizontal direction when prepared using the slurry method, whereas they are oriented in the random direction when prepared using the compaction method. Attempts were made to evaluate the extent of anisotropy exhibited in slurry and compacted samples using the measured pore water pressure measured during the undrained loading. So the A over here, it's the slope of the effective stress path. And this graph plots the secant A value with axial strain for all slurry samples and compacted samples at 3 values of confining pressures. For the slurry samples, the A value becomes positive at axial strain less than 1%. That is because, as we see over here, the fibers are already aligned in the horizontal direction. So once shearing is initiated, tensile stresses mobilize in the fibers, the overall horizontal stiffness increases, the effective stress path deviates to the left with a negative slope and a positive A value. The A value for the compacted samples remained negative throughout the shearing, and that is expected due to the random orientation of the fibers due to the higher compaction energy supplied during the sample preparation. Now, moving on to the shear strength of the fiber reinforced clays. The overall shear strength of the fiber reinforced clay is a combination of 3 components. The strength due to the interaction between clay particles, strength by the interaction between clay particles and fibers, and finally, due to the tensile stresses mobilized within the fibers. Any initial increase in the deviator stress that we see over here is due to the interaction between clay particles. The increase in deviator stress between the linear elastic and linear strain hardening response, or we can say the increase in the deviator stress during this transition is due to the frictional interaction between fibers and clay particles. Any increase in deviator stress during the linear strain hardening portion is only due to the tensile stresses mobilized in the fibers. So once shearing is initiated on the fiber reinforced clay soil, the deviator stress increases, the pore water pressure increases, the effective stress path deviates to the left, increasing the overall horizontal stiffness of the composite. But once the pore water pressure is equal to the effective confining pressure at which the sample is sheared, the effective stress path approaches the tension cutoff line. For the effective stress path to cross this tension cutoff line, or for any further tension to mobilize in the fibers, the pore water pressure has to exceed the minor principal stress, which is the cell pressure in a triaxial compression test. This condition of pore pressure greater than cell pressure cannot be achieved by performing a consolidated undrained compression test, and that limits the amount of tension mobilized within the fibers and subsequently limits the shear strength of overall shear strength for clay composite. So in any of these tests, we were not able to measure the maximum tensile stresses developed in the fibers, and we were not able to bring the samples to failure or measure the maximum shear strength of the composite. In addition, the stress strain graph shows a strain hardening response without a well-defined peak, so that again limits the potential to define the strength for this class of material. So that is considered as one of the major limitations of a CU triaxial compression testing program. Now moving on to the conclusions of the study, all samples of fiber reinforced clay exhibited a strain hardening behavior and bulging response when tested up to an axial strain of 20%. The greater amount of bulging in slurry samples was due to the greater freedom for the fibers to move and mobilize tensile stresses. The compacted samples are prepared at their optimum moisture content and maximum dry density. So they demonstrated higher values of deviator stress during shearing. Greater rate of increase of pore water pressure was observed in slurry samples, and this is due to the increased amount of tension mobilized in the fibers when prepared using the slurry method. Greater amount of tension was mobilized in 18 millimeter long fibers compared to 6 and 48. And for all 18 millimeter long fiber reinforced composite, the pore water pressure developed at the end of shearing was equal to the effective confining pressure, and the effective stress path followed the trace of the tension cutoff line. Examination of the transparent fiber reinforced clay confirmed that the predominant fiber orientation is horizontal in slurry samples, whereas it's random in compacted samples. And from the normalized probability distribution chart, we confirm that the fibers in slurry samples are oriented at angles between 0 to 40 degrees, whereas the fibers are inclined at angles between 0 to 90 degrees in compacted specimens. Performing a triaxial compression test limits the ability to quantify the maximum tension in the fibers and curtails the potential to define the strength for this class of material. This signifies the necessity to perform more tests along varying stress paths to define the shear strength behavior of a fiber reinforced clay soil completely. These are the references used in the study. And thank you so much for your attention.
All right. I do have some questions from the audience and myself as well. So the first question, for the transparent soil that you are using, how have you or did you establish a similitude or similarity between the transparent soil and the EPK kaolinite, such that any conclusion that you drew from the transparent soil would also be applicable to, I guess, the pure kaolinite soil as well? Like, have you done any comparison in terms of critical state line and stress strain behavior, etc.?
Yeah, so for the transparent clay that I used for the study, it's made from fumed silica. So there are a lot of studies done previously on this fumed silica transparent clay. And the researchers have already proved that like the shear strength, consolidation, and hydraulic conductivity of this transparent clay is similar to the natural clays. So it's not like, you cannot say like it is similar to like kaolinite clay or bentonite clay, not one clay in particular, but the macroscopic properties are similar to most of the natural clays. And that is the reason why we use the same product, fumed silica, for this study, because we want to have a soil surrogate that helps us to visualize internally how the fibers are oriented within the mix.
Okay, thank you. I guess the recipe for that transparent soil is just taken from the literature, right? Just
exactly
kind of with known properties. So that's
yeah. So basically, how it works is like the fumed silica, it's having properties similar to the natural clays. And when you disperse this fumed silica in a pore fluid combination of matching refractive index. So in our study, we use like a combination of white oil and a mineral oil. So what we are doing is we are just matching the refractive index of these two materials. So it looks transparent. So basically when light passes from the solid to liquid interface. There is no refraction, there is no scattering, and it appears homogeneous to light, and we see it as transparent. So it's the same recipe from the previous studies because they have already done triaxial test, consolidation test, and hydraulic conductivity test. So they know like this composite can be used to model a clay soil. So that's why we use the same recipe from previous studies.
Thank you. So the second question is related to the orientation of the fiber.
Yeah.
I think he's asking the
Sorry, Tony, I can't hear you.
How do you determine for the orientation angle of the fiber?
Okay.
Yeah. So the question is, how do you determine precisely the orientation of each fiber to generate that curve? I think.
Yeah. Can I share my screen? I can like show you how did I get the orientation.
Yeah. Yeah. I think you have the access. So
I do. Thank you. So this is like the polyline detection tool that we have in MATLAB. So it's basically like you have three vertices. You can click and drag between each and every line in this image, and you get the inclination of every line. So for example, this is oriented at 46 degrees. And if I move to this line, it is oriented at 85 degrees. So basically, you do it for all the lines in the images. And here you have the inclination of all the lines. So this is kind of the method that was adopted for compacted and slurry prepared transparent clays to get the inclination of these lines. And then you basically place it in the Excel and draw the probability distribution curve.
Sorry, I think my internet is breaking out a little bit.
Sorry?
I think my internet is breaking up a little bit.
Yeah, even in the presentation, I feel like my voice was breaking. So that's why, I tried to contact you. Like, I don't know if you need any further clarification for any slides, please ask me, because in my end, it was like breaking.
Yeah. Okay. Thank you. That explains it. So you essentially use manual, kind of a manual counting.
Exactly.
To figure out the angles. Yeah. Okay.
Yeah.
Next question. Related to the fiber content. So 2% fiber content used for all the samples, right?
Yeah.
The question is, what if when applying, if you apply a lower dose or higher dose of fiber compared to that 2%? So if you apply like 3% or 1%, will that dosage influence the geotech behavior of the sample in a dramatic way? Like, have you thought about that? And that's the first part of the question. The second part of the question is, if you add a longer fiber, could the length of the fiber be offset by a lower dosage? So I think the question is focused on the dosage, and if that dosage is gonna have any combining effect with the length of the fiber together. So if you use a longer fiber, maybe you can get away with a lower dosage, for example, or a higher dosage with a shorter fiber, for example. I think that's the question.
Yeah, I think I got it. Yeah. So for this study, like not included in this paper, but I have tried 3 dosages of fibers, namely 1, 2, and 3%. So when I increased the fiber content from 1% to 2%, there was an increase in the shear strength and pore water pressure response. And that is expected because we have more amount of fibers, which means there is like more area of contact between the fibers and the clay particles, which increase the interface frictional strength between fibers and clay. And also greater amount of fibers means there is more tensile stresses developed in the fibers, and that again contributes to the shear strength. But when I increase the fiber content from 2% to 3%, I saw a reduction, like a dramatic reduction in the strength and pore water pressure. what we are assuming is like when I increase the fiber content beyond 2, there might be a tendency for the fibers to kind of cluster inside the soil sample rather than getting distributed uniformly. So if we imagine in that way, what happens there is like the shear among the individual fibers becomes the dominating factor than the tensile stresses in these fibers. So that was the reason why we saw a dramatic reduction in the strength and pore pressure when I increased the fiber content beyond 2%. So that is the reason, like for all tests in this study, the fiber content is kept constant at 2%. And with regards to the fiber length, again, the same way, as we increase the fiber length from 18 to 48 millimeter, there is like greater area of contact and greater interface friction between the fibers and clay. And previous studies on fiber reinforced sand already proved like the pull-out resistance of the fibers increases with increase in fiber length, and also the amount of tension mobilized in the fibers also increase with an increase in the length of the fibers. So this reduction that we see is only due to the scale effects factor, because my sample diameter is 50, and if I try to add 48 millimeter long fibers into it, it might just get bent and twisted inside the sample. So these are the two variations that I tried in the study, the fiber content and length.
Thank you. So it's quite, I guess it's quite sensitive to the fiber content, because you said if you increase from just 2% to 3%, is that by weight, I assume, or by?
Yes, it's actually by the dry weight of the clay soil.
Right. So, and you see something drastic in the properties. So I guess.
And it was observed in both samples, both the compacted and the slurry samples. We saw this reduction if the fiber content was increased beyond 2.
Oh, okay.
Yeah.
And I guess your sample size is also a big part, because
it could be,
it's quite limited. Yeah,
exactly. All my tests are on 50 millimeter diameter samples, so that might also be another reason.
Yeah, I saw your your sample extracted from the slurry. They have cracks here and there. I guess it's kind of difficult to extract a perfectly intact sample from the Shelby tube, right? Because of the cracking and the insertion process.
Yeah.
So it's challenging.
Getting these samples from slurry method was really challenging, because we have a very good fiber soil block, but pushing these Shelby tubes into it was challenging, because the fibers do show a tendency to kind of get carried along as you push the Shelby tube. So I had to work with the tubes again, make sure like it's really thin, it's oiled inside and outside, and one end is flat. So so it was a bit challenging to get good samples for triaxial testing from the slurry method.
Okay. The next question is on compaction. So what compaction energy or what kind of compaction did you use for the compacted sample? Is that a standard Proctor, like using mold, or is that using higher energy, like a modified Proctor compaction?
Yeah. So initially for the compacted sample, I was using the standard Proctor test, where I have a big mold and then I push LB tubes and get samples for the testing. But the major issue over there, like wastage of my fibers, wastage of effort and time. So that is the reason why I moved to this 2-part compaction mold. So maybe just give me a sec.
Yeah, I think you can share.
Yeah. So can you see my screen?
Yes.
Yes.
Okay, thank you. So for the compaction method, I am not able to quantify what is the compaction energy used. All I can say is like the soil fiber lot was placed in this compaction mold, and we used this rammer, and it was placed as 5 layers, and each layer was subjected to 15 blows by using the arbor press. We don't know what is the weight of this hammer in the arbor press, so I'm not able to quantify the compaction energy. But I can say that you can prepare a good compacted sample by using the standard Proctor method. Even that works, it's just a wastage of our resources and time and energy.
Right. And use the consistent compaction method for
Yeah,
all the
definitely.
sample, right? Yeah.
So to make sure like the variability is minimum, what we did is we prepared the soil fiber lot, like the whole 4 kg in one day, and it was saved in the moisture room for at least 48 hours. And all 6 samples were prepared at the same time. So just to make sure like there is no variation between like sample to sample. Yeah.
All right. Thank you, Akhila. I didn't see any more questions from the chat. So I think that's all the questions we have so far. Still have lots of time, so please
Sure.
don't be afraid to type questions, or I guess you can unmute yourself if you have any burning questions. I have a question.
Sure.
So have you considered doing the consolidated drain test to determine the dilatancy and then perhaps at a higher confining stress for the critical state line?
No, I have not done any consolidated drain test with this. I mean, at least in this paper. The reason was my main objective was to measure what is the pore water pressure developed within the sample and what is the extent of anisotropy. So if I want to evaluate what is the extent of anisotropy, I can only get it like based on the effective stress path. What is like the slope of the effective stress path? And the reason why I did testing from 50 to 200 kilopascal is because for all these applications that we are saying, like this composite is applicable, for example, evapotranspiration covers and slopes. So this was the variation in the normal stress values. But I have done some drain test on this composite using the Bishop-Wesley stress path triaxial test that we have currently in the Mindwaste lab. The reason for those drain tests is to see like how fibers influence the yield envelope of a clay soil. So over there, what we did is like we did testing along different stress paths. So basically projecting the stress path to different regions of the stress space and getting the yield points, combining that and try and draw the yield envelope. So all those tests were drained, but again, in none of these tests, I was able to bring the sample to failure or define the critical strength. Because like for the axial strain, at least like till 20% axial strain, the deviator stress was showing a strain hardening behavior. There is no peak, there is no failure in the samples, and none of them reached the critical state line.
Oh, okay. Yeah.
Yeah. And the only way where we can like define the strength, we are thinking like one potential option where we can define the strength is by doing the triaxial extension test. Because the major thing is we are not able to bring these samples to failure because in a compression test, the minor principal stress acts in the horizontal direction. It's actually the cell pressure. So once the pore water pressure becomes equal to the cell pressure, it's not able to exceed any further or for any further tension to mobilize in the fibers. So all we can do is like reversing these stress paths. So in an extension test, minor principal stress acts in the vertical direction. So you can increase the pore water pressure in excess of the minor principal stress, but still less than the confining pressure.
Right, because your fiber is oriented almost sub-horizontally. So if you do extension, then you mobilize that strength.
Exactly.
Quicker,
We're expecting like we'll be able to bring the sample to failure and define like the peak strength and critical state for this material.
That's right, that makes sense. I got another question from the audience. I don't know if this is related. It's asking if there's any kind of transparent soil for sand as well, like or have you?
Yep. Transparent sand, if I'm not wrong, it's made by using silica gel. So so it's basically different components of silica. Here we are using silica powder dispersed in pore fluid combination to develop transparent clay. But you can use amorphous silica gel to develop transparent sand. And there are a lot of studies done on geogrid pull-out test on transparent sand. It's really interesting. You can actually see like what is the displacement profile near the geogrid sand interface by using a pull-out box, which is transparent, and by using the digital image correlation technique.
Okay, thank you.
Yeah, it is also applicable to the pile failure mode. Like people have done studies to see what is the influence of this driving shoes and surface rips on the displacement profile. You can actually visualize the mode of failure. So that's the best thing with the transparent soil.
So it's the same minerals, but yours is powdered, like grinded or pulverized to powder. Then the other is just intact gels, the various diameters, right? Yeah.
You can vary the pore fluid combination, like you can use a white oil and a mineral oil, or a combination of 2 mineral oil. And some have even used calcium bromide and water. The only thing is you have to make sure the refractive index of these two materials match, and it's transparent. So you can visualize what's happening there. Yeah.
All right. Okay, I've got more questions. So is there any way to extract the compacted? I think it has to goes back to the orientation of the fiber. So is there any way to extract the compacted sample from a different orientation? And from there, you evaluate the anisotropic stress strain response. So instead of doing extension, I guess if you extract the sample from another orientation, then test from there. Have you thought about that, or
extract the sample? So the study
from a different, let's say right now you're extracting your sample from a vertical direction, and if you extract it from another orientation and another angle, maybe.
Yeah, that's what I'm doing right now. So what I have here is like the soil fiber block where the fibers are oriented horizontally, and I'm extracting sample from it and doing testing. So basically, the effective fibers are maximized when they are oriented perpendicular to the direction of major principal stress. So the major principal stress in a triaxial compression test acts in the vertical direction, and you get the maximum effect from the fibers when they are oriented in the horizontal direction. Right now, as a part of my research, I'm doing triaxial extension test on samples. So what I'm doing is, I'll take the soil fiber block as such, I flip it and extract fibers which are vertically oriented and then do extension test. So I'm not in a position to comment about the research as my soil fiber block is still consolidating, but it's actually the study which I'm doing right now to see like how does the change in fiber alignment affect the strength and pore pressure response.
Thank you. That's very interesting. Yeah.
Yeah.
Okay. I don't see any other questions right now in the chat box. So I think we're good to wrap up this session. Fernanda, do you have any final words, or?
No, I think we can end the meeting today, and we'll see you guys next week.
Thank you, Akhila, for the presentation. It's a great one. We enjoyed it. For all the students, we'll see you next Wednesday at the same time.
Yeah, thank you, Akhila.
Thank you, everyone. Yeah.
Thank you, everyone. Bye-bye.
Bye.